Welcome to today's explainer. Look, I want you to start by just imagining a world where electricity is so incredibly abundant that your monthly power bill basically becomes a thing of the past. Imagine an energy revolution so profound it literally changes how we power our lives forever. Well, that is the promise of fusion energy, and today we're going to unpack exactly what it takes to get there.
I mean, it sounds like pure science fiction, right? What if a single glass of seawater could provide enough energy to keep your home running for years? But scientists all around the world are currently racing to make this astonishing scenario a reality. They're trying to literally bottle a star to create a virtually limitless, clean energy source. If they succeed, it wouldn't just be a technological leap. It could easily become the greatest energy revolution in human history.
Okay, let's dive into this explainer. Here is our roadmap. First, the ultimate energy dream. 2, how fusion actually works. 3, fusion versus fission. 4, bottling a star. And 5, the future we could build.
Part 1, the ultimate energy dream. Let's look at why we have such a desperate need for change in the first place.
Which brings us to Part 2, how fusion actually works. And to really figure this out, we have to look up at the sky.
Every single second, our sun releases a mind-boggling amount of energy. But you know, it isn't just burning fuel like some giant campfire. Deep inside its core, tiny hydrogen atoms are violently colliding and combining to form an entirely new element, helium. This is nuclear fusion. It's not about burning material to ash at all. It's about smashing atoms together under immense pressure.
And this is exactly where Albert Einstein's famous equation comes to life. See, when those hydrogen atoms fuse, a tiny bit of mass is lost. So where does it go? Well, it converts directly into energy. Because of that c squared, representing the speed of light squared, even a microscopic amount of matter produces an absolutely staggering amount of energy. It is quite literally the engine of our solar system.
Moving to Part 3, fusion versus fission. What exactly is the difference here?
Now, what's really interesting about this slide is how we can break this down. You're probably familiar with the nuclear power plants we use today. Those rely on fission, which works by splitting very large atoms apart. Think of it like taking a massive, pre-built Lego structure and just smashing it to release energy. Fusion does the exact opposite. It's like taking tiny, individual Lego pieces and forcefully snapping them together. And as a nice bonus, with fusion, there are no rogue Legos left on the floor for you to step on in the dark.
This difference in the physics matters immensely because snapping those small atoms together offers massive, world-changing advantages. With fusion, we're talking about zero greenhouse gas emissions during operation. The fuel sources, like the elements derived from seawater we mentioned earlier, are incredibly abundant. It produces much less long-term radioactive waste compared to fission, and structurally, there is no risk of runaway chain reactions, meaning those traditional nuclear meltdowns are physically impossible. In theory, fusion is one of the cleanest and most powerful energy sources imaginable, which obviously leads to the question, why aren't we using it right now?
Well, that brings us to Part 4, bottling a star. This is the ultimate challenge.
The answer as to why we aren't using it yet is surprisingly simple: gravity. See, the sun has immense gravity that naturally creates the intense pressure needed to force those repelling atoms together. Here on Earth, we completely lack that gravitational advantage. And unfortunately, we can't exactly order a gravity well on the internet. So scientists have to figure out how to recreate those extreme conditions entirely artificially.
And because we lack that stellar gravity, we have to compensate with extreme brute force heat. To make fusion happen here on Earth, the fuel must be heated to over 100 million degrees Celsius. Let that sink in for a second. That is literally hotter than the core of the sun itself.
Now, when you heat matter to over 100 million degrees, it doesn't just melt or turn into a gas. It becomes a superheated, highly charged state of matter known as plasma. This plasma is the specific environment where fusion reactions can actually occur. But creating it, that's only half the battle. The nearly impossible task is keeping this violently energetic, superheated plasma stable for long enough for the fusion reactions to actually take place and generate usable power.
So the crucial point is this. Researchers are essentially attempting to hold a miniature star inside a machine without letting it ever touch the walls. If that superheated plasma touches the reactor walls, it instantly cools down, the reaction dies, and the machine could be severely damaged. It is an incredibly delicate engineering tightrope.
To solve this, scientists and engineers around the world are locked in a massive race, building huge experimental reactors to test out different methods. And the two primary methods are actually really fascinating.
First, some teams are building enormous donut-shaped machines that use incredibly powerful magnetic fields to trap and confine the plasma, basically suspending it in midair so it never touches the walls. The second major method involves using arrays of incredibly powerful lasers, focused precisely on a tiny pellet of fuel, to instantly trigger the fusion reaction through rapid compression and heat.
And despite the crazy odds, we are seeing incredible progress. Recently, researchers achieved a monumental milestone. For the very first time, a fusion reaction produced more energy than the energy used by the lasers to trigger it. Net positive energy. I mean, many experts thought this was still decades away, but it proves the core concept actually works on Earth.
All right, part 5, the future we could build. Let's look at a world transformed.
Because progress is accelerating so fast, we really have to start seriously thinking about commercial viability. What does everyday life look like if we actually master this? Imagine your own world transformed. We're talking about major cities powered 24/7 by clean energy, completely unaffected by the weather. Imagine limitless electricity for your electric vehicles, drastically cleaner air, and reliable power lifting up remote, developing communities all around the globe.
But I do want to keep this explainer grounded in reality. Despite all this excitement, fusion is still not a completely solved problem, and it isn't arriving tomorrow. We have to acknowledge the major hurdles that remain. Scientists and engineers still desperately need to improve the overall efficiency of these reactors. They have to drastically reduce the astronomical construction costs of building these facilities. They must invent and develop entirely new, highly durable materials that can withstand these extreme, star-like conditions for years on end. And ultimately, they have to figure out how to scale up these brief laboratory successes into continuous commercial power plants.
However, even with those massive challenges, the sentiment in the scientific community has fundamentally shifted. Many experts now echo this powerful sentiment. It's no longer a question of if fusion will work, it's a question of when. That is an inspiring level of certainty coming from the people who know this science best.
Let's move to and see how this builds into the grander narrative of human history. Civilization has always advanced through massive leaps in energy technology. We discovered fire, engineered steam engines, and leaped from early electricity to nuclear fission. Each step radically transformed the world. Fusion is simply the next logical, giant leap. It's a technology capable of providing clean, abundant energy for generations to come.
The dream of creating a star on Earth might sound impossible, but every single day, scientists are moving us closer. The incredible power that lights our world today might one day be generated right here in our own backyards. The only question left is, will you be ready when we finally plug into a star? Thank you so much for joining me for this explainer, and keep your eyes on the future.